valve settings on the energy consumption of the machine. And for doing this, I introduced two working cycles. They are exactly the same. They are composed of 5 stages. And the first is just with the machine unloaded, and the second one is the machine loaded. And by measuring the consumption of the machine, we can see how an efficient configuration of these valves can actually allow the machine to save about 30% of the energy. But of course, as I said, this is not free. And you can see this in this plot. For this particular operation, where we can see the pressure profile in the first plot and the acceleration of the boom in the second plot, where here I'm just comparing an energy inefficient setting of the valve with a good dynamic behavior, with a very efficient setting of the valve, but as you can see, a very excessive oscillation content of the motion. And of course, the natural step forward was to apply the controller to the energy efficient configuration of the machine, and to show that the application of this controller can bring back the machine to a stable behavior while saving energy. So now we demonstrated that a general approach for reducing the oscillation of the machine implements or the machine mechanical parts is possible. But for example, for this kind of machines, they are load handling machines, so they handle loads, the stability of the load is of major interest. And this is a problem of many applications. So the second part of my PhD was focused on addressing the oscillations of the payload. And in order to do that, I tried to extrapolate more information from our sensors. And so what we have used so far are the time domain information of the sensor. But actually, the frequency content of a signal contains much more information. So what I did, I tried to use these informations in order to address the payload oscillations. And if we think to the machine as a multi-body system, we can recognize different subsystems in this machine. So the first subsystem can be represented by the main boom actuator with the rest of the machine, which can be modeled as an equivalent mass acting on the cylinder. The second subsystem is the actuator, the outer boom actuator with the rest of the machine, again acting as an equivalent mass. And the third subsystem is the payload itself. So in order to understand how the oscillation of the payload is reflected in the pressure, which is what we are measuring, I made a kinematic study of the machine. So taking as a reference the machine in this position, we can simplify the kinematics in this way. And if we assume the load motion has sinusoidal, as for example a single pendulum, we can write the acceleration in the x and y axis of the payload. And this was really interesting because from these two equations we can see how the oscillation of the payload is reflected to the pressure in a frequency way. So the x acceleration contains actually 1 and 3 times the frequency of the oscillation of the payload, while the y-axis contains 0, 2, and 4 times the payload oscillation. And just another side note, the zero frequency does not really exist, because if you would imagine a zero frequency, that would mean that we have a constant acceleration of the payload, which will lead to a drift, an indefinite drift of the payload. And this is difficult to demonstrate analytically. What I did, I used the Fourier transform of these two terms, and you can show that the sum of these two terms is 0, so that means that the constant term at 0 omega 2 does not really exist. So, since acceleration is force and force is pressure in the cylinder, in order to better understand how this acceleration is felt by the actuator, I made this plot where actually I didn't make this plot, Ricardo made it, and where here what we are plotting are the 4 components of the frequency we saw before, so 1, 2, 3, and 4 times acceleration of the payload. And on the x-axis, we have the amplitude of the oscillation of the payload. And we can see how these frequencies are actually also present in the experimental measurement. Where here, those are is an FFT of a pressure sensor measured experimentally, and we can recognize again 1, 2, and 3, and 4 times the payload oscillation frequency. So now the question is, can we use this information? And I mean, I would say the answer is of course yes, but which one? So as we can see here, 3 and 4 times the payload oscillation frequency, they are very small, so they are difficult to use for a feedback. And now, so the two oscillation at 1 and 2 omega 2, this is something we can use. But as we will see in the result, unfortunately, the payload oscillation is exactly the frequency we want to move the machine in order to stop the payload oscillation. So it's something that we are going to affect with the control of the machine. So we cannot directly use this information. While 2 omega 2 is something that we can use because we are not affecting directly this frequency with the control of the machine. And this is explained much better in my thesis here for time constraints and not explaining the whole process. So by using these considerations, a very straightforward way to address payload oscillations is to generate a sinusoidal excitation of the machine in order to stop this oscillation. And that's what I did as first step. And for in this particular topic, I would like to thank Riccardo Bianchi, who was a visiting student here, now PhD student. He helped me quite a lot on this topic. And so here is the controller strategy we implemented. So again, we have this low-pass filter logic where we just use this low-pass filter and this logic here just to select which pressure we want to use. So once the pressure is selected, we perform an FFT estimation and a peak detection. So with the FFT also, the FFT is not something tricky. We had to use some windows and we had to manipulate the pressure signal. And this again is explained in much more details on the thesis. And the peak detection block just detects the peak associated with the payload oscillation. So now we extrapolate the information about the amplitude of the double frequency of the payload oscillation. And what we do, we just generate a sinusoidal command to the valve in order to generate a sinusoidal motion of the boom. And those two parameters, so the amplitude of the sinusoid and the phase, is something that we have to optimize. And to do that, we use the same optimization process, and then we use again the same gain scheduler approach, except for the fact that now the gain scheduler is indexed again by the operator command, but now is indexed also by the frequency, the oscillation frequency of the payload, and the low pass filter pressure. And so the output of this gain scheduler indexes these two parameters. And so in order to show the effectiveness of this controller strategy, what I did, I defined a working cycle in order to make a very repetitive experiment on the brain. So here is the cycle where in the first stage, and this is the operating condition I'm referring to. So in the first stage, we just excite the machine in order to generate an oscillation in the payload. The second stage is just a short pause. And the third phase is the controller action, which is something you can see in this video where we have in the first stage, again, the excitation of the machine in order to realize the oscillation of the payload. Then we have a small pause and then the controller action. And another important thing is how to evaluate the oscillations, or how to evaluate the effectiveness of the controller. And I did this by using the definition I'm about to say, and here is just an example, a result example, where if we define two different peaks of this oscillation, separated by a number n of periods, we can define a logarithm decrement, and then we can define an equivalent damping ratio. And this is a fairly commonly used technique in order to calculate damping ratio. I want to use this information just to estimate the effectiveness of the controller. So I will compare the damping ratio or the equivalent damping ratio of the machine without controller and controller. And here you can see the results for, so this, as you can recognize from the previous slide, this is the result, and this is the acceleration measured with an accelerometer placed on the payload. And here is the control command, and here is something interesting which validates what I was saying about the 1 and 2 omega 2. So here the blue line is the harmonic at exactly the same frequency of the payload in the pressure, while the red line is the harmonic at twice the frequency of the payload. And as you can see, once the controller starts, the red line is actually decreasing in the same way the payload acceleration is decreasing. But the blue line, which is the frequency at the same frequency of the payload, is actually increasing and then decreasing. And this is exactly why we cannot use this frequency, because the controller is actually affecting this pressure, this information. And here in this video you can see the comparison between the two methodology with and without controller, and you can also see the maintenance curve. And so on the, of course, on the right we have the machine with controller. So just to give an objective number of the damping ratio increase of the system caused by the controller, I calculated about 4.5 times increase. So now, as I said, this technique is very effective, as we saw, and is also, I don't know what I was about to say. Anyway, the problem with this technique is that it's based on the FFT. And the FFT is something difficult to use in a real-time way, because as you all know, the FFT is something that is made for stationary signals, while we are actually measuring transient oscillations. So what I try to do as a second step is to try to find a different formulation. So still using the frequency information contained in the pressure in the pressure sensor, but for example by generating a particular filter in order to use the time domain signal from the sensor to isolate the oscillation of the payload and to generate a command to the machine. And this is what I did. So again, we have the same logic for the pressure sensor selection, and then we still have the FFT estimation and peak detection, but now the FFT estimation just gives us an estimation about the location of the oscillation and just if the oscillation actually exists or not. And so now we take the pressure and we use what I implemented is these two filters and modulation, which I'm going to explain in the next slides. And the result of these two filters and modulation is the output, which will be superimposed to the operator command. And again, this technique is based on a gain scheduler, and again is indexed by the operator command, low pass filter, pressure, and frequency of the payload. And now the gain scheduler changes the parameters of these three blocks. Excuse me. So what are these three blocks? So the notch filter is just a particular filter which is very useful when we want to cancel a specific frequency from a signal. So here you can see the transfer function of this filter, where this Q is an important parameter, because as we increase Q, we are making this filter sharper, and so we are removing better or more sharply that frequency. But what I need is actually the opposite, right? I want to isolate a particular frequency. So what I did is just what I call notch pass filter, but in literature is also found as peak filter, where what I do, and this is the actual implementation, is 1 minus n minus 1, the notch filter. And here, just for completeness, is the discrete time implementation, where now R and Q are basically the same parameter, but now R is between 0 and 1, and by changing R, we are changing the poles of this transfer function. So how this works? So here we have an example of a general operating condition where we have the acceleration of the payload, the pressure sensor, and this is the content of the frequency content of the pressure signal. So as we can see, we have two spikes at 0.5 and 1 Hertz. So applying the filter, we get this as signal which contains 2 times the payload oscillation. And now, unfortunately, we cannot use this signal as direct feedback, because now it's a feedback at twice the frequency of the payload, while we want to move the machine at the same frequency of the payload in order to stop the oscillation. So what I did, I simply used the trigonometric formulas to modulate this signal. So in order to extract the information at 1 omega 2 from this signal. And so assuming that the signal is a sinus, but it can be also a cosinus, which is the double payload frequency, we multiply times a cosinus at 1 omega 2, and then this is what we get. And this is actually from a real signal, from a real case where we have the payload oscillation, which can be a sinus, double the frequency of the payload plus a phase that we have to compensate. And then we have twice the cosinus of omega 2 plus the phase of the FFT, which is something calculated in real time, plus a phase, which I call the phi c, which is the phase we have to optimize in order to counteract these oscillations. So and this is the result. So we have the filtered pressure, we have the augmentation, and then we have the output feedback. Now we have the signal at the same frequency as the payload, so which is something we can use as feedback. And now we of course have this part here at 3 times the frequency, and this is something we want to remove because we don't need it. And in order to remove this, what I did,